Example 5 here is a little more theoretical. It's asking us to use indicator variables and linearity of expectation to prove that the expected value of a hypergeometric random variable is little n times little r over capital N. So this one's a little more theoretical. We're going to prove this value, so we can't just quote it from the earlier slide. Let me show you how this works out. Remember the premise of the hypergeometric distribution. We're calculating a random variable that represents the number of women on a committee of little n was the number of people on our committee. That's little n, number of people on our committee. And we have several parameters here. Capital N is the total number of people in the room that we're going to pick from. So total people, total number of people. Among those total number of people, R is the number of women, and N minus R is the number of men in the room. Capital N minus little r is the number of men. And then we're going to pick a committee of little n people, and we want to find the expected number of women. Now, there's a very clever way to do this, which is to set up indicator variables. So let me show you what I mean by indicator variables. Let me define y1. By definition, is an indicator variable. So let's consider that we're going to pick these people to be on our committee one by one. So we look around the room and say, I want you, 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 and you to be on the committee. So we're picking these people one by one. Y1 is going to be an indicator variable that tells us whether the first person on that committee is a woman or not. So Y1 is defined to be 1 if we get a woman on the first pick. So we pick our first person to be on the committee. Y1 is an indicator variable. It's going to be a 1 if it's a woman, 0 if it's a man. You can think about it, it's a little strange, but you could say Y1 is the number of women we get on the first choice. So we either get 1 woman or we get a man, so that's 0 women. And then we'll define Y2 to be 1 if we get a woman on the second pick. So the second person we look at, if that's a woman, we say Y2 is going to be 1. If it's a man, we say Y2 is going to be 0. Now, let's keep on going. Now, we're picking little n people to be on this committee. So we go up to Y little n here. We define all our indicator variables. There's one variable for each person on this committee. Now, what that means is Y is the total number of women on the committee. Number of women. So what that means is it's the number of women we got on the first pick, which is either 1 or 0, number of women we got on the second pick, up to yn. So the total number of women, we can count the number of women just by counting all the ones we got by those indicator variables. So it sort of breaks down into a sum of these indicator variables. So in order to find the expected value of y, the expected number of women, it's the same as the expected value of y1 plus y2 up to yn. And now we can use linearity of expectation. So this is where we're going to use the linearity right here. Linearity of expectation. Very important here. By the way, these variables are not independent, but linearity of expectation does not require that. So even though these variables are not independent, if you get a woman on the first pick, you're less likely to get a woman on the second because there's fewer women to pick now. But even though they're not independent, you can still use linearity of expectation. That's kind of the glorious thing about linearity of expectation. So it breaks up into the expected value of each of these indicator variables. Now, what is the expected value of each of these indicator variables? So let's think about that. I'll give you a good way to think about that. If you think about, let's just think about Y1. We pick one woman out of a crowd. And so the original definition of expected value is you look at all the possible values of that variable and you multiply that variable times the probability of getting, you multiply that value times the probability of getting that value. So this is going back to the original definition of expected value. I covered this in one of the very early lectures, so on probability. You can go back and look at some of those early lectures on probability and you'll see this. But what are the possible values of these indicator variables? Well, there's only 0 and 1 because we said up here that the indicator variable is always going to be 0 or 1. So this expands out into 0 times the probability of 0 plus 1 times the probability of 1. And, well, what's the probability that an indicator variable is going to come up 0? It's the probability that we get a man, because the indicator variable was 0 if we get a man, plus 1 times the probability that we get a woman when we make our first pick. And now, well, I don't care about the 0. The probability of getting a woman, well, how many people were there in the room? There were capital N people in the room, and little r of those people were women. So this is exactly little r over n. That's the expected value of one of those indicator variables. It's just little r over capital N. But now we can say that all of those indicator variables, they all have the same expected value. So each one of these is little r over capital N, r over capital N, and there are little n of these variables. So what we get here is little n times r over capital N. And so that is the expected value of our random variable. That's the expected number of women on our committee. And of course, that checks with the value of the mean that I gave you way back on the third slide of this video. So that's really where that number comes from. Now you have the derivation to back it up, and now you hopefully understand it yourself. So in case that didn't make sense, a quick recap here. N was the total number of people in the room, capital N. Little r is the number of women, which leaves capital N minus r to be the number of men left over. We're going to pick a committee of little n people, and y, capital Y, is the number of women we get on our committee. But one way to break that down is to look at our picks one by one. We pick this person, and then that person, and then that person, and then that person to be on our committee. Each person, we set up this little indicator variable that's going to be 1 if we get a woman, and 0 if we get a man. So each person has their own indicator variable. And that means the total number of women is just the sum of all these indicator variables. It's the sum of all the women that we got when we made each one of these picks. And so the expected value is the expected value of the sum. Here's where we use linearity of expectation. That's kind of a big deal in probability, so let me highlight that. To break that up into the expected value of each of these indicator variables. But we can calculate the expected value of these indicator variables. We just say, well, the only possible values they can take are 0 and 1. So using our original definition for expected value, we have 0 times the probability of 0, 1 times the probability of 1. So we really only need to calculate the probability of 1, which means the probability that we get a woman when we pick a certain person from this room. Well, there's r women in the room, and n, capital N, total people in the room. So the probability is r over capital N. So we fill that in fill that in for each of our expected values here. It's the same for every indicator variable. So we're adding up a bunch of R over capital N's. We're adding up lowercase n of them, and so we get lowercase n times R over capital N as our answer. And of course, that checks with the mean of the hypergeometric random variable that I gave you back earlier on in this lecture. So that's our last example problem, and that wraps up our lecture here on the hypergeometric distribution. You are watching the probability videos here on Educator.com, and my name is Will Murray. Thanks for joining us. See you next time. Bye-bye.